Welcome to MSP lecture series on main group chemistry. In my previous lecture, I spoke on oxides of group 13 elements. Today, let me speak on halides of group 13 elements. Boron trihalides are monomeric under ordinary conditions and possess trigonal planar structures. They are much more volatile than the corresponding compounds of aluminum. The trifluorides of aluminum, gallium, indium and thallium are non-volatile solids best prepared by the fluorination of the metal or one of its simple compounds with fluorine gas. In fact, when we talk about trihalides of group 13 elements, all combinations of M and X occur in trivalent MX3. That means, when we consider MX3, all combination are possible where M equals boron, aluminum, gallium, indium and thallium, and X fluorine, chlorine, bromine and iodine. Okay. So, all combinations are possible with an exception of thallium triiodide. The reason is very simple. Any combination of highly oxidizing and highly reducing species is unstable, and here thallium plus 3 is essentially oxidizing in nature and I minus is reducing. So, as a result, what happens? This one is unstable. Except for this one, all combinations are possible, and as I mentioned, all trivalent halides are planar molecules and they have an empty p orbital perpendicular to the plane in BF3 and in fact also in BCl3. These pi back donation from filled X pi orbital. That means, you just recall chlorine or fluorine, okay, when they have acquired an electron, they have S2p6 electronic configuration. Out of that one, that means 4 pairs of electrons are available in the valence shell of any halide anion. Out of that one, if one pair is utilized in bonding, other 3 pairs are available for pi bonding. Out of that, one of the fluorine can always, okay, donate through 2 pi or 2 pi 3 pi interactions to overcome some of the electron deficiency of boron atom, and in this case essentially boron fluorine bonds have some multiple bond character more compared to BCl3. Here in case of BCl3, we are talking about a 2p and 3p overlapping, and because of mismatch this overlapping is very poor. As a result, what happens? A poor back bonding one can anticipate from chlorine to boron. As a result, what happens? Boron trichloride remains more stronger or powerful Lewis acid compared to BF3. Okay. So, you just recall the MO diagram I showed for BF3 molecule while discussing the bonding concepts. That time I showed you this one, this I wrote MO diagram for BF3. Here you just see B can utilize 4 valence orbital. So, 2 p orbitals and 2 s orbital, whereas here this F3 fragment has 12 orbitals, essentially each one has 3 p and 1 s. So, as a result, total of we have 12 ligand group orbitals. These ligand group orbitals will combine with B to form this bonding and non-bonding. That means, essentially we have total of 16 atomic orbital. Out of 16 atomic orbitals, 4 atomic orbitals are used for bonding and 4 for anti-bonding, and remaining 8 remain as non-bonding with 16 electrons. You may be wondering from where these 16 electrons are coming. Just go back to this BF Lewis dot structure. Okay, of course, this is planar. So, we have this kind of situation here. We have 3 pairs of electron on each. Let us assume one of the fluorine atom gives a pair of electron through back bonding p pi p pi. So, then still we are left with 1, 2, 3, 4, 5, 6, 7, 8. That means 8 pairs of electrons. 8 pairs of electrons are still left, and these 8 pairs of electrons are essentially occupying here. This one pair, whatever is there, that is participating in bonding, can be seen here in this one. This is the one that is responsible for, that is essentially coming from Pz, that is perpendicular to the plane of the molecule, where Px and Py are combined with S to form sp2 hybrid orbitals. Okay. So, you can see here, and in case if you write similar MO diagram for BH3, we are considering H3 fragment here. So, in this case here this will not be there, because it accounts for only 6 electrons, 3 electrons from S2P1 of boron and 1 electron each from hydrogen. So, that essentially comes for 6 electrons. Okay. So, this one is essentially coming from one of the fluorine lone pairs. So, that is making it multiple bond character in one of that one. So, that essentially gives or satisfies the octet of boron, okay, and remaining 16 electrons are placed here, they are non-bonding. So, BX3 are monomers. Okay. The structures of AlX3, that means aluminum trichloride fluoride, dependent on the type of halide we are using. Aluminum trifluoride is a high melting polymeric solid built from fluorine bridged AlF6 octahedra. The structure of AlCl3 in the solid state has 6 coordinate aluminum centers with chloride bridges. However, in the liquid and gas phase, aluminum trichloride remains dimeric, that is called Al2Cl6, with dative bonds between aluminum and chlorine in the bridging unit. I will be showing those structures soon. Aluminum tribromide and aluminum triiodide are dimeric in all states. Okay. So, before I show the structures, let us see how one can prepare some of these group 13 halides. All boron trihalides except Bi3 may be prepared by direct reaction between the elements. However, the preferred method for BF3 preparation is the reaction of B2O3 with calcium fluoride in sulfuric acid. You should remember calcium fluoride is a powerful fluorinating agent. So, let me write these reaction methods through a balanced chemical equation. Similarly, the reaction between boron and chlorine or bromine yields BCl3 and BBr3. For example, in case of BCl3, when it is treated with Hi, it can give Bi3 plus 3HCl. Or one can also start with sodium borohydride plus 8 equivalents of iodine. It gives so, this is how one can prepare bismuth triiodide. Let us look into the nature of these halides of boron, and BF3 is colorless gas, boiling point 172 Kelvin, and BX bond distance, BF bond distance is 131 picometer. In BCl3 is a colorless liquid, boiling point 285 Kelvin, melting point 166 Kelvin, and bond distance is 174. BBr3 again colorless liquid with boiling point 364 Kelvin and melting point is 227 Kelvin, and here BBr distance is 189 picometer. Boron triiodide is a white solid with melting point 316 Kelvin, and the boron to iodine bond distance is 210 picometer. So, all are planar molecules. And tetrafluoroboric acid HbF4 is essentially a very strong acid, and it can be prepared by conveniently mixing HF with BF3. It is a very strong proton donor. However, the very strong proton donor is essentially a combination of HF plus SbF5. This is HbF6. This is a much more stronger proton donor compared to this one, and if you consider BF4 anion, this is very similar to PF6 anion, and they coordinate very weakly to metal centers and is often used as an innocent anion to precipitate larger cations, especially those of transition metal complexes. So, boron trifluoride forms a range of complexes with ethers, nitriles and amines. That means essentially they are all having donor atoms such as nitrogen or oxygen, and of course, commercially BF3 is available as etherate. Multiple bonding or partial double bond character can be seen from this diagram here. You can see here, as I said, when in a typical planar molecule, if you consider so these are all pz orbitals. We have electrons here, and here this is empty pz orbital. So, here one can see interactions, and this results in multiple bond character, and in case of boron we can anticipate 2p interaction, 2p pi interactions. The formation of partial bonds in trigonal planar BX3 molecule can be considered in terms of the donation of electron density from the filled p atomic orbitals on the x atoms, that is halides, into the empty 2p atomic orbitals on boron. So, reaction of BX3 with Lewis base results in a change from a trigonal planar to a tetrahedral molecule. In that case, what happens essentially, instead of forming sp2 hybridization, it forms sp3 hybridization having 3 sp3 orbitals having 1 electron each and 1 sp3 having no electron. So, this without any electron will interact with filled 2p orbitals of fluorine or 3p orbitals of chlorine to form multiple bonding or have a pi bonding like this. You can see clearly here. Of course, when we talk about multiple bonding between boron and fluorine is much more stronger compared to boron and chlorine, because here we are talking about 2p with 3p interaction. Because of the mismatch of the orbital, overlapping is not very efficient, whereas in case of boron trifluoride we are talking about 2p interaction. Here the overlapping is more efficient. As a result, what happens, BF3 somehow overcomes the electron deficiency compared to BCl3. As a result, BF3 is slightly less Lewis acidic in nature compared to BCl3. So, this shows the reactions of boron halogen compounds. For example, you can see here BX3 can react with water to form boric acid, BOH thrice, or you treat that one with alcohol to form corresponding alkoxide or aryl oxides, or one can treat with amines to form adducts, or one can also treat with dialkyl sulfide or diaryl sulfide to form the adduct again similar to amine adducts, and when it is reacted with phosphine also forms adduct, and similar adducts are also known with carbon monoxide as well, and on treatment with amine it undergoes proteolysis to form this kind of compounds BNHR 3 times. Okay. These are some reactions of boron halogen compounds, and boron chlorides, bromides and iodides are susceptible to hydrolysis by mild proton sources such as water, alcohol or even amines that you saw. So, just let me show one reaction here, although I had shown in that previous slide. Okay. And whereas BF3 forms an adduct with NH3 and BCl3 reacts in liquid ammonia to form BNH2 3 times, whereas BF3 simply forms an adduct. The preparation of alkyl boron or aryl boron compounds is essentially starting from the corresponding boron halides. For example, BF3 on treatment with methyl magnesium iodide can give trimethyl boron. Of course, plus you get magnesium halides such as so MgIF, and similarly one can also treat BF3 with methyl lithium. Methyl lithium is a tetramer, so one can write like this. It gives so one can write either Me or one can also write CH3. So, boron halides containing boron-boron bonds also have been prepared. The best known of these compounds are essentially B2X4. Okay. So, for example, B2Cl4. Okay. So, this is essentially a planar molecule. One can also make similarly B2F4 as well, or B2Br4. Okay, so here you can see in solid state B2F4 and B2Cl4 are planar molecules, you can see here, whereas vapor phase BCl2 units are orthogonal to each other. So, one of the BCl2 becomes orthogonal or it will be perpendicular to the another BCl unit, and of course, B4Cl4 has a structure like this where 4 boron atoms are disposed to 4 corners of tetrahedron, and here these are all chlorine atoms. And metathesis reaction can be used to make these B2X4 derivatives. The thermal stability of these derivatives increases with increasing tendency of the X group to form pi bonds with boron. So, one can write the stability in this order: B2Cl4, B2F4, B2OR 4, okay. And these B2Cl4 at higher temperature can give higher analogues of boron halides. For example, B2Cl4 when it is heated to 720 Kelvin, within few minutes it forms B9Cl9, or on heating this one to 373 Kelvin in presence of CCl4 over several days, it gives B8Cl8. Okay. And B2Br4 adopts a staggered conformation in the vapor, liquid and solid phase. Of course, the preference of this one is not clearly understood. B2Br4, unlike B2Cl4 or B2F4, adopts a staggered conformation in the vapor phase as well as in liquid as well as solid phase. These preferences are not readily understood or can be explained. Probably one can anticipate that because of the larger size, when they are planar, probably that leads to the bromine-bromine interaction. To prevent that one, instead of like this, instead of something like this, okay, it becomes something like this. So, if you assume this is boron, B boron and another one, instead of like this, it becomes like this, so that bromine atoms can move away from each other, giving a staggered conformation. Okay. So, let us look into now aluminum, gallium, indium and thallium halides. These trifluorides are non-volatile solids and compounds are obtained by direct combination of the elements, again treating aluminum, gallium or indium with the corresponding halogens. One can make these trihalides, and they are relatively volatile in the solid state, possess layer lattice or lattice containing dimers of the type M2X6. Only at high temperature they dissociate to monomeric MX3, and solid AlCl3 adopts octahedral structure. I will show you the structure. Okay. Before I show the structures of all these halides, let me show the methods of preparation of these halides. Al2O3 on treatment with 6HF, it gives AlF3 plus 3H2O. So, the preparation of anhydrous aluminum chloride can be planned using one of the following methods I am going to write. For example, you can treat directly aluminum with dry chlorine gas, should be very dry, to get anhydrous aluminum trichloride. Of course, if it is hydrated or it is wet, one can also sublime aluminum trichloride to get anhydrous aluminum trichloride, and repeated sublimation can give you ultra pure very dry aluminum trichloride. One can also use aluminum oxide and chlorine in presence of carbon as a reducing agent. Okay. One can use carbon or carbon monoxide. So, when you use carbon monoxide, you get carbon dioxide, and aluminum trichloride reacts towards moisture. For example, it can form aluminum oxide, can let me show you the structures now. So, here in aluminum trifluoride, each aluminum center is octahedral surrounded by 6 fluorine atoms, each of which links to aluminum centers in a linear manner. So, having angle close to 180. The octahedral AlF6 unit is encountered in other aluminum fluorides. So, if you just look into the monomeric unit, it looks in this fashion. For example, if I consider so, it continues like this. Each monomeric unit will be having this kind of linear one. Of course, I can tell you why it is linear, whereas in case of chloride it's little different. You can see here we have a bent structure here, okay, and this is that solid state. In liquid state and gaseous state it exists in the dimeric form, whereas in solid state it is hexa coordinated in this fashion. You see, this is how it is there. You have a layered structure something like this, and that can be seen here in this one. So, you have a layer structure where each aluminum is 6 coordinated, and these chlorine atoms again make bond with the neighboring aluminum in this fashion, and this layer structure continues. And the question is why in case of aluminum chloride we have a bent structure like this, whereas in case of aluminum fluoride we have a linear. This has to do something with the size of the halides. If you just see here, the size of this one is little bigger, something like this, okay, and here it is much more bigger. So, one can expect them to have this kind of overlapping here. Of course, here we have lone pairs, whereas in case of fluorine because of the smaller size, if we try to make a bent structure, we have to force 2 aluminum atom come very close, and your fluorine will sit somewhere here because of the smaller size. Because of this situation, what happens? These two will start repelling. 2 cations coming very close together will repel. As a result, it is destabilized. Instead, okay, they prefer to have this kind of okay. So, here cations are kept away from each other. For this reason, most of the fluorides have linear structure, and to have a polymeric structure, they have to be, the monomers has to be minimum of trimeric, but mostly they prefer tetrameric structure, whereas in case of chlorine one can always anticipate bent angles at chlorine atoms. Okay. Cryolite is essentially Na3Al(F6) that occurs naturally, but can also be synthesized to meet the commercial needs, and also in case of electrolysis of aluminum oxide to get aluminum. So, the solid state structure of cryolite is related to the perovskite lattice, and one can conveniently prepare starting from aluminum hydroxide, treating with HF in presence of sodium hydroxide. It gives Na3Al(F6). H2O. So, when water is dripped onto solid aluminum trichloride, vigorous hydrolysis occurs, but in dilute aqueous solution it forms (3+ and okay, with NH3 aluminum trichloride forms an adduct in the solid state, and of course, in this one there is intermolecular hydrogen bonding is there that exists as a result of this kind of interactions. Okay. Some intermolecular hydrogen bonding is anticipated. Okay. So let me stop here, and let me continue in my next lecture more about gallium and indium trichlorides, tribromides, and also their lower halides. Thank you very much.